This presentation is titled "A Computation of the Covariance Between Two Linear Statistics for the Jellium Model." And to begin, we're going to give an overview of some methods that are provided in a paper from a European group that's provided in the references of this archive posting, in which we're going to further build upon their methods to provide a formula for the Jellium covariance function, which they mentioned could be of interest from some approximations to a probability measure that they introduced, which we're going to describe at length. And to provide this formula for the covariance that they predict or that they anticipate that their methods can be useful for, they introduce a probability measure for the Reese gas, from which we'll have to introduce a rescaling of the Boltzmann weight. And associated with the probability measure on the eigenvalues of a matrix, we're going to have to make use of an effective saddle point action whose approximation is related to rate function. And the rate function is going to be used for a large deviation argument. So this is an overview of all of the quantities that we're going to make use of in study to provide a formula for the covariance of the Jellium model between two linear statistics. So first, we have to begin with the energy function of the Reese gas. And to define the Reese gas energy, we're going to be looking at a model that's one-dimensional on the real line. And we're going to be looking at the position of xi for some collection of positions on the real line, from which the energy function of the Reese gas, which is given by E sub k of these from 1 to big N points, is given by capital A over 2 times the sum of the squares of each one of the positions of the particles on the real line, plus alpha times the sine of k times a summation for I not equal to j of the absolute value of xi minus xj raised to the minus k. And so this energy function is going to correspond to the energy of the Reese gas. And many times when one introduced Hamiltonians and different energy functions in statistical mechanics, it's important to keep in mind what is the order and relative magnitude of any of the prefactors which come in front of any terms of the Hamiltonian, and also the summation over different positions, as we've given here for xi squared and xi minus xj to the minus k. And in this case, both A and A, which appears in front of the first term, and alpha, which appears in front of the second term of the energy function for the Reese gas, are assumed to be of order big O1. And besides the terms that we had introduced in the energy function for the Reese gas that's given in the previous slide, there's also a sine of k term, which is defined to be 1 if k is greater than 0, 0 if k is 0, and minus 1 if k is negative. Strictly negative. And we also have to introduce a conformal transformation over the position of each one of the particles of the Reese gas on the real line. So for that, we're going to introduce some conformal transformation T of x, which from complex analysis, the usual requirements that we enforce and that we require of this function is that AD minus CB is non-zero. And it sends the position of each one of the particles to some eigenvalue lambda I. So we're going to be introducing a probability measure for the Reese gas from this energy that we defined in the previous slide. And then we're going to use that formula for the probability measure to obtain a probability measure on the conformal image of the transformation T on each one of the points xi that the gas occupies, that the particles of the gas occupy on the real line. And as we had just been mentioning, to transition from the energy function to defining the probability measure, we can introduce another definition, which the authors in the European group make use of, which is namely that the probability measure, boldface P, on each one of the lambda i's is given by the reciprocal of the partition function times an exponential of minus of the Reese gas energy, which we introduced 2 slides ago, normalized by the Boltzmann constant times the temperature. And the partition function that we introduce in this probability measure on each of the lambda i's, so that the exponential of minus the energy normalized in the Boltzmann constant times the temperature is given by this summation over all possible I. So it's given such that over all coordinates or all positions I such on the real line such that I is less than or equal to big N. So it's just a summation over each one of those, over the square of the eigenvalues lambda I squared and the absolute value to the minus k between lambda I and lambda j, such that I is not equal to j. And as we had alluded to previously, the temperature which is involved in the kBT, which is given by the reciprocal of the energy function in the power of the exponent, is also of order 1. So we're introducing some assumptions on the order of the temperature that we would like to have in the probability measure, as well as the order of the parameters big A and alpha, which also have to be order of 1, as we had mentioned earlier. And we can look at a special case of the Jellium partition function for k is equal to -1. And this corresponds to a rescaling of the Boltzmann weight, because the k parameter in the energy function for the Reese gas appears from the fact that there can be this minus k term appearing in the difference between the eigenvalues lambda I and lambda j. And this just comes from looking at the image under xi and xj under the conformal transformation t that we introduced. So this is giving a different type of partition function for some value of k, namely k is equal to -1, in which we just substitute -1 for each one of the values of k, which appear in the not only in the energy function for the Reese gas, but also in the normalizing constant through the partition function. And the partition function for k is equal to -1 satisfies this equality, in which one can introduce a factor lambda or L of big N as a prefactor to each one of the lambda i's, which ends up making a contribution to the position of the eigenvalue I squared. So there's a lambda n squared, as well as a lambda n contribution, which appears in the absolute value in the reciprocal, the absolute value difference between the eigenvalues lambda I and lambda j. And from this rescaling of the partition function, one can introduce a particular case of the general probability measure that we introduced for the Reese gas in the previous slide, and that which we will denote p twiddle, which is given by boldface p, which was the probability measure that we defined in the previous slide, in which each one of the lambda i's are scaled by L of big N. So this is given by a very similar expression to what we had introduced earlier, with the exception of the -1 assumption through the rescaling of the Boltzmann weight comes into play in the partition function, as well as the energy function, which appears in the power of the exponent for the definition of the probability measure of the Reese gas that we gave for general k. And we can also define the linear statistic, which is given by the fact that we can take a linear statistic as a summation that takes the following form, which we'll denote with little s. And for some strictly positive integer big N, it's given by a summation of f of x sub I divided by 1 over, or divided by n, for an arbitrary real function f of x over the real line. And we can define the covariance formula from the Gibbs-Boltzmann weight, and this provides a general form for the covariance formula that we'll be able to write a precise expression for, that will come up in the end of the presentation. And the covariance formula from the Gibbs-Boltzmann weight is the following. We're going to introduce, for some non-empty subset lambda to the big N of the real line, the following expression between the two linear statistics A and B. So we introduce a linear statistic A over N, but we can also introduce another linear statistic B, which is instead given by a summation over some smooth function over the real line little g instead of f. And the covariance between these two linear statistics is given by an integral for the first term, in which we integrate against each one of the lambda I over some non-empty over some non-empty subset of r to the n, the reciprocal of the partition function for k is equal to 1 times the exponent of the energy function for k is equal to 1, as well as multiplying A of t of x1 through xn and B of t of x1 through xn, and subtracting off the expected value of the product of these two linear statistics. So these terms A and B, which appear under the integral over Rn against each one of the lambda i's, is given as a function of the image of the points x1 through big X or x big N, as well as under B, in which we multiply the values of these two linear statistics so that we can compute the covariance between them. And the expectation value, which we give here, which we provide, which we subtract off from this integral over Rn, is a function over the real line, but we just drop that dependence from the notation. And the following arguments that we're going to give is an overview of what the paper from the three authors makes use of as an overview of the Coulomb gas method, in which we want to introduce a probability measure on the linear statistic little s that we gave, which is a summation of 1 over n times the sum over n points of f of xi. And this is given, again, as an integral against each one of the lambda I of p twiddle, which is itself a function of each one of the lambda i's that we map to from each one of the xi's under the conformal transformation t, as well as some delta function. And we're going to really make use of the effective saddle point action and the large N deviation argument to re-express and approximate different terms of this probability measure that's a function of n, which is going to be making use of the large N deviation, and which is also a function of the linear statistic little s. And we can approximate the probability measure with the exponential of the rate function. And the rate function is another quantity that's introduced in their paper, because the authors make use of the fact that this probability measure that's a function of big N in the linear statistic can be approximated by the exponential of minus n cubed times the rate function, where the rate function can be approximated by the reciprocal of 1 over 2b for some strictly positive constant b times the square of s minus s bar. So it's just measuring the square difference between s and the mean s. And this function, this rate function, achieves a minimum at s is equal to s bar. And the variance of the linear statistic is approximately given by b to the n over 3. So by making use of these two components for the rate function, namely what the variance of the linear statistic can be and how this relates to the rate function that we can use to approximate the power in the exponent for the probability measure script p, we'll be able to make use of the effective saddle point action as well as a large N deviation towards providing a formula for the covariance between two linear statistics in this model. And we can recall that that the probability measure on the linear statistic script p can be approximated with in one of the terms that's given by the delta function, in which the delta function over each one of these i's can be together approximated by n cubed given by the integral over some path of big gamma 1 over 2 pi exponential minus nu n cubed, which is taken in this integral is taken with respect to the measure d mu. And we can introduce a normalization for the measure script p on the eigenvalues, in which from the previous slide that we gave, we're able to re-express the power of the exponent, which is given in the reciprocal of the probability measure, which is relating to the effective saddle point action and the rate function, which are the quantities that we've been introducing from the paper that we've been referencing and wanting to extend their methods and make use of their methods for, in which the power of the exponent is given by a minus n cubed, where this term that's given besides the minus n cubed scaling is given as an expectation with respect to mu of some density rho of x that's supported over the real line, minus n times some Shannon entropy type term, which is rho of x log rho of x for the density over the support over the support for this density function rho of x, as well as another delta function, which is given instead that is proportional to the integral of d of x rho of x minus 1. So we can introduce, for this k is equal to -1, rescaling of the Boltzmann weight that we introduced earlier in the presentation, an integral with respect to each one of the lambda i's of an exponential of this power that's informed by properties of the rate function and the large n deviation that we're going to make use of. And the integral with respect to each point that the Riesz gas occupies can also conveniently factor as the following, in which if the support is given by the support sub I over n such of these sets, for the support of each one of the particles that's given by the Riesz gas, we can write the integral of d rho of t of x as a product from i's between 1 and n over each one of the support sub I with respect to the measure d rho of t of xi. And the effective saddle point action is a function of the density and mean, in which S, which is the effective saddle point action, is a function of this rho of x guy, which we introduced for the density before, as well as mu, which is the mean, and some fixed mu naught. And this is given by 3 or 4 types of integrals, in which the first integral is just given over the support of the density rho of x, while the second integral is given over 2 copies of the support of the density rho of x, because we're integrating rho of x rho of y times the absolute value of x minus y dx dy. And the 2 other terms are given as integrals over the support that are either proportional to the constants mu, or the mean mu, or the constant mu naught. In incorporating the effective saddle point actions and approximations for the probability measure script p that we mentioned in previous slides, yields a probability measure of the form below, in which we can approximate the probability measure script p from the effective saddle point action, in which the support of the probability measure, which corresponds to the product of the supports over each one of the xi that the Riesz gas occupies over the real line, as a product over 1 is between I and n, as well as an integral over some path gamma over the real line with respect to d mu, as well as another term with respect to d mu naught, which represents which is representative of the exponential of minus n cubed times the saddle point action. So we basically introduce, building upon the paper in the reference that's provided in the link for the description of this video, how the authors anticipate that their methods for doing particular types of computations for the Jellium function can be adapted for forming the covariance between 2 linear statistics for the Jellium function, in which we replace the power of the exponent with the effective saddle point action. In the Jellium covariance, which is the main computation that goes into this paper, is of the following form. So we first take 2 linear statistics, A, where A is a function of f and each one of the big N points, x sub 1 up to x sub n, as well as another linear statistic B, which is a function of the function, or B, which is a function of the function little g, as well as the points, each one of the points xi. And the Jellium covariance between A and B is given by this reciprocal of n squared times the integral against the support of d rho of x times the terms with respect to d mu and d mu naught that we introduced in the previous slide when approximating the probability measure script p on the linear statistic, as well as multiplying the values of f of xi and g of xi over the summation from I is equal to 1 to n, and finally subtracting the expected value with respect to f and with respect to g. And n is given by a strictly positive parameter, and f and g are arbitrary functions over the real line. And the large deviation function that we've been mentioning several times throughout this presentation can be approximated by the fact that in the power of the exponent, which we use to define the probability measure of the Riesz gas, for k is equal to -1, this term in the power of the exponent can approximately be given by n cubed times the effective saddle point action, where rho mu star of x denotes the saddle point density action, and the rate function can be expressed in terms of a contribution from the effective saddle point action in a 2/3 alpha squared term. So conclusions for this presentation that I wanted to provide before closing out is that we began by making use of a paper due to a group of authors in which they raised the possibility of defining the Jellium probability measure from the Reese gas energy function. And from this definition of the energy function and the probability measure that they first provide, they introduce a conformal transformation that acts on the positions of each particle of the gas, which allows us to obtain a probability measure on a slightly different quantity for each one of the lambda i's. And we introduced the saddle point action and the large deviation action, or argument for approximating script p, which is the probability measure on the linear statistic. And then we provide a formula for the Jellium covariance, which follows from a general formula that they indicate can be of interest of the covariance between two linear statistics that are supported as functions over the real line. And thanks for listening.